I'm going to give an example of logistic regression. The key thing about logistic regression is it's the same as fitting a usual line to a set of data where you predict y from x, except in this case y is either 0 or 1. You either have the disease or you don't. So in this case there are 100 patients of different ages and you've got whether they have coronary heart disease or not. I could do a scatter of this. So if I go to chart builder and I do a scatter plot and I pop this on. So if I have whether they have coronary heart disease or not on the y-axis and I have their age on the x-axis and I press OK. So this will show me that you have lots of dots on one saying they've got it. So they're less frequent at lower age, they become much more frequent at higher age, and then the opposite, those that haven't got coronary heart disease are much more common at the lower ages and much more frequent at the higher ages. So what you want is a sort of curve that goes along here and then transitions somewhere about here between the two. So it's going to go along and there'll be an S-shaped curve and go up and then into the top group. So what you're doing is fitting this curve that will connect those two parts of the graph. So to do that in SPSS you go down to Analyze, go down to Regression, and it's an example of a binary logistic regression. Now in this case the dependent variable, my y, is coronary heart disease, which is the yes or no thing, zeros or ones, and the x-axis is just age. That will be whichever variable you have which you think is predictive of your binary outcome, your yes-no outcome. For options, I've asked it to work out the confidence interval, and I've clicked on Hosmer limit show goodness of fit, but let's get rid of that. So that should do okay. Continue, and you press OK. That's the entire process done. So it's telling you how it builds the model. So this is telling you what the variables are within the equation when it sets it up. Now if I go down to the bottom here, this is the variables in the equation once it's fitted the data. So that's the starting point, and this is the fit. So it tells you that the b, which is the kind of equivalent to the slope, but it's used as a predictive thing, is 0.111. The lower confidence bound is 1.066, the upper is 1.171. The constant is minus 5.309, and the thing that you want to look at is the significance. So in this case it's telling you that age is significantly related to coronary heart disease, and there's definitely a significant relationship which you can build based on this. So this is the b value, which is because it's based on a logarithm. You anti-log it to get the exponential b value. So these are the things that depend on age directly, and this is the variable that depends on the log of age. I forgot to say about one other thing that you need to look at, which is the model summary. So here you've got likelihood, don't particularly worry about that. But these are your R-squareds calculated by the Cox and Snell's methods or Nagel-Kirk's method. These are 0.254, 0.341. They're relatively low. You prefer them to be above 0.5. It's not a fantastic model because it's not got other variables included. So there's going to be many other factors. So the R-squared tells you how much your x variable is predicting the variability of the y. So this one's saying that it's predicting about 25.5% of the possibility of getting coronary heart disease, and there's other contributions which contribute about 75%, and this one's saying it's contributing about 34.1%, so there'll be another 65% from other factors.